Alright, hello and welcome back everybody. This is problem number 10 from a Physics C Mechanics multiple choice test. Um, Personally, I think this is the hardest problem on the test, and some of my friends have agreed with me. So, up top, I have just the context of the situation that applies to problems both 9 and 10. And you can check back in my last video if you want to hear me read it out loud. Here's problem 10. Which of the following equations could be used to find R minimum, the minimum distance between the masses as particle A approaches particle B? So remember, we have these two particles. Initially, B is at rest, and A is moving at speed v0 towards B. So here we're being asked to find the minimum distance between the masses as A approaches B. So using this equation, when R minimum, when R is at its smallest, that's going to make potential energy at its greatest, because the smaller the R is, the greater B over R squared is going to be. So here we know that potential energy is at its max. We also know that when potential energy is at its max, that's when kinetic energy is going to be at its least. So the minimum, R minimum, is going to be when potential energy is at its max and kinetic energy is at its minimum. Because when the kinetic energy is at its maximum, there's no kinetic, or when the potential energy is at its maximum, there's no kinetic energy in the system. The energy is all stored in potential. Alright, once we have this, we're going to start looking at the equations. So these equations are just energy equations. So this, B over 4D squared, this is an equation for potential energy because look, it mirrors this. So D here, it represents distance. So we can just label these. These are all of these. They're all the same, and that represents potential energy. Then these next terms in all of these equations, these represent kinetic energy, which, just for reference, let's write this out. Kinetic energy is equal to 1/2 mv squared. So right away we know kinetic energy is 1/2 mv squared. Some of these don't have that half of it in it. They've dropped part of the kinetic energy equation. Let's get rid of the ones that lack that 1/2, which is a part of the equation for kinetic energy. So we can cross off A and D right away. Now we're going to skip to the end of the equation. So this front side of the equation represents the initial energy in this system. Now the right-hand side of the equation represents the energy in the system when R is at its minimum. So yeah, this is a hard problem. Let me. Okay, so momentum is going to be conserved in the system because there's no external forces. Because of that, we know that the velocity at the end of this situation, when R is at its minimum, is going to be the velocity of the two particles is going to add to v0. So because of conservation of momentum, we can say v0 is equal to the A final plus the B final. And we know, again, going back to the kinetic energy part of this, we know that kinetic energy is at its minimum. So for kinetic energy to be at its minimum with 1/2 mv squared, we're going to want the v's to be as small as possible because they're squaring. So for this to be the case, we can split v naught into 1/2 v naught and 1/2 v naught, and that's going to give us the smallest possible ke values. Stay with me here. So from this, we know that the velocity of particle A and B when r is minimum is each going to be 1/2 v naught. And now going back to this equation, again, this tells us potential energy at the end. This tells us kinetic energy at the end. So we're going to look for, okay, first of all, two of these equations lack any kinetic energy at the end. But we know by conservation of momentum, these particles can't just stop moving because there's energy in the system. So we can cross off D because it doesn't have a kinetic energy term at the end of the equation. Now we've narrowed it down to just B and C. So let's compare these two terms. So here we have the 1/2 v naught squared, which is what over here we've decided is going to be able to minimize kinetic energy, because we know that that's going to be at a minimum when r is at its minimum. And also, so basically the difference between this is here the 1/2 is on the outside, here the 1/2 is on the inside of the square with v naught, which is correct because here this is also adding the kinetic energy of the two particles. Each one at the end is going to have a kinetic energy of 1/2 m 1/2 v naught squared. So when you have two of these times 2, these are going to cancel out, and it's just going to be m 1/2 v naught squared, which is what we have right here. So thanks for watching. I hope this helps. This shows us that B indeed is the correct answer. So this question requires you to have a really good understanding of how variables relate to each other in an equation. It all starts from this right here. U, potential energy, is equal to B over r squared. And knowing that when r is at a minimum, that's going to make potential energy a maximum. And then being able to convert in your mind between potential, kinetic energy, and being, of course, having this equation memorized, you've got to know what kinetic energy equals, you've got to know what potential energy equals, and be able to think about how they relate to each other. So thank you for watching. Hope this video was helpful, and check back in again for number 11. Thanks.